In this segment, we're going to talk about evaluative models for performance and cost. Now, an evaluative model at its basic level takes in our design variables and predicts our cost and performance attributes. Typically, these models also calculate a number of intermediate variables about which we may have interest. Now, earlier we described the design value mapping technique, where we represent the relationship between design variables and attributes in a matrix. Entries in the matrix had a 0, 1, 3, or 9 that represented the degree of impact a design variable is expected to have on an attribute. Now, this is not a model, but it is a first-order representation of our mental model. For example, entries that have a 9 are those in which we expect there to be a strong impact between the design variables and the attributes. This means there are likely relationships that need to be modeled in our evaluative models. In this particular example for a satellite system, we can see 4 clusters of strong relationships. These represent orbital mechanics, both easy and hard, communication systems design, and the impact of the number of satellites on performance. Using a DVM in this way allows us to focus on particular areas where we should spend effort for developing our evaluative model. Once we have these areas of interest, we can brainstorm modules that evaluate our design variables. We can then create an n-squared diagram that represents how information flows between these modules, and then partition our effort to develop software code. In our satellite system example, we had 7 modules: orbits, spacecraft, launch, mission scenario, cost, attributes, and utility. The flow diagram illustrates the relationship between these modules, how information flows between them. As another example, consider a space tug system, which is implemented in a low fidelity. Our value model is a multi-attribute utility function. For our performance model, we use simple linear sums for our intermediate variables of mass. This included calculation of our propulsion system mass, our bus mass, our dry mass, our wet mass, and then our 3 attributes, a delta V capability and speed. Delta V was calculated using the rocket equation. Capability and speed were calculated using lookup tables. The lookup tables were populated using existing data. For our cost model, we used a simple mass-based relationship for estimating cost. Now, depending where you are in the life cycle, you have different availabilities of data. Early in the life cycle, we often have to use lower fidelity models because we don't have enough information about the problem at hand. It's important to use the DVM and similar techniques to prioritize our modeling efforts. If there's a weak relationship between our design variables and our attributes, we should not spend a lot of time and effort modeling the relationship. It's because ultimately the impacts can be very little on the value delivered. As we move through the life cycle and we get more detailed in the relationship between design variables and attributes, we can spend more time and effort in modeling those relationships. In terms of a good enough model for trade space data, this is really a judgment call in terms of your confidence in the model and the types of questions being asked. Traditional best practices for developing software should be used, including verification and validation. Comparison against existing systems, if possible, is always useful, as is comparison against existing products. Additional considerations that should be taken into account when developing these models is looking at the sensitivity of assumptions to the outputs. If expected sensitivities do not exist, then perhaps one might reformulate the problem. There are many different techniques for developing particular performance and cost models. Further information on particular performance and cost models can be seen in the supplemental materials.